Alright, best C++ code ever written. You all wanted more, so here we are. If you have no idea what I'm talking about, check out the first video here. Someone sent in some code that they claimed was the best C++ code ever written. And of course, that leaves me trying to figure out whether or not it is. Now, whilst I do want to get back to taking a look at all of the actual code that we have in this project, which by the way, I'll have linked in the description below, what I want to talk about today is specifically the way that this board is represented in data, in memory, because memory and data layout is one of the most important things in programming. And to be honest, that together with the operations we perform on that data, the way that we transform that data, is all that programming actually is. So today, let's have a look at how this is put together, how it works, and whether or not we can learn something from it. And of course, a quick little disclaimer, I've never written a chess engine before, I've never really researched chess engines before, so my knowledge here is very superficial, and I'm going to be focusing mostly on the actual C++ code instead of the way that this chess engine is put together. Now, that being said, this is interesting to me because the actual chess engine here runs on bitboards or UN64Ts. I've mentioned this very, very briefly in the last video, but I want to expand on this a little bit more. So we know that a chessboard is 8x8, which perfectly maps into 64 bits, meaning that each position on the chessboard, each square, is 1 bit. Now, immediately this kind of makes sense as a possible representation of a chessboard because, well, there's 64 bits and we have 64 squares. However, each one of these bits is, well, 1 bit. So that means that it can either be 1 or 0. Now, immediately that doesn't give us much of a representation, right? We basically can either have a square marked as 1 or 0. Without any additional data, we don't know anything more than just 1 or 0 for a particular square, which is why you can see that it says here the board is represented in just 12 UN64Ts. So we have 12 here, 1 for every piece, where each bit represents a piece on the board. So we basically have 12 of these. Each bit represents a piece on the board, but remember it can only be 1 or 0. So in other words, we don't know what piece it is. We can't possibly store that. We just know, is there a piece there, which presumably is 1, or is that square completely blank? Is it empty, which would be 0? And so rather than storing the board information from like the point of view of the board, meaning that we have variables which describe the board, in which case we would definitely need more bits to represent, for example, which particular piece was at a particular square. Instead of looking at it from that point of view, we instead look at it from the point of view of each piece. Now, why are there 12 pieces? Because in chess, we have more than 12 pieces. Each side technically has 16 pieces because we have 8 pawns and then 8 other pieces. That times 2 for both sides means that we have 32 pieces on a chessboard. And in fact, the quantity of individual piece types can also change because if we get a pawn to the very end, we can promote it into a queen, a rook, a bishop, a knight, whatever we want. And so it's possible, say, for white to have more than 1 queen. However, if we disregard duplicates and we just have a look at how many unique pieces there are per side, then we have 6 unique pieces per side. We have a pawn, we have a rook, we have a knight, we have a bishop, we have a queen, we have a king. And then of course the rest of the pieces here, which I've marked in blue, are just duplicates. Multiply that by 2 because we have white and black and we get our 12 number. Now, if you're interested in learning programming, but you're finding it difficult to stay engaged, then I might just have the perfect thing for you. Boot.dev. Boot.dev takes inspiration from modern game design to make learning backend development way more fun and interesting. They have hands-on practical lessons that balance theory really well with practice, so you can learn backend web development from start to finish in the Python and Go programming languages. And they've got loads of courses. One of the most important things I talk about when learning programming is just how important practice is. When learning anything, really, you can't just sit there and keep taking in theory, you have to actually put this into practice and start programming. Which is why I love that when you're going through these Boot.dev courses, every step of the way you need to write actual real code to implement solutions to problems. And they tie this in with game-like systems to make all of this a lot more fun. So you'll earn XP, level up, complete quests, etc. If you get stuck and you need some help or you just want a deeper explanation to something, they have this Bear Wizard AI chatbot that's trained on all of their content, which you can always talk to. And yes, you will have to give him salmon. Another great thing is that all of their content is completely free to read and watch in guest mode, so you can check it all out first. You'll need a paid membership to access the interactive interactive features such as the actual hands-on programming. There's loads more to discover, so head to boot.dev and check it out for yourselves. You can also use code Cherno to get 25% off your entire first year if you choose the annual plan. Huge thank you to BootDev for sponsoring this video. And so as I mentioned, we're storing the board representation from the point of view of the pieces. And another really crucial detail here is that squares cannot have more than one piece on them. So even though we have multiple pieces of each type, we still can't have a square being occupied by more than one piece, which is important because if we could, this wouldn't work. And so for each piece type per side, for example, the bishop, we have 64 bits that represent where it is. So if we start with 2 bishops, they might be over here and over here for our starting position. So those bits would be 1s and everything else would just be 0. For something like our pawns, we start with 8 pawns and they would be here, so all of these bits would be 1s and then the rest would be 0s. And this concept is something called a bitboard, where we just store the board's representation like this as a series of bits per piece. Now the reason why I bring this up and I want to talk about this is because clearly this is somewhat of an optimization that must work really well with the rest of the algorithms that manipulate or transform this particular data. We always want to structure our data based on the way that it's going to be transformed. Now, when I say the word transform, I don't literally mean it's going to be changed into something else. It could be read and presented in a different medium. So a really quick example of that might be we have an array of pixels that make up an image, but then we have to read them to actually present them onto our screen, onto our monitor, using our graphics card. So that might not seem like transforming to you because we're not really changing that data into something else by manipulating the actual bytes that represent it, but a piece of hardware is literally going to read that data and then present it in some other format for us to look at. So I really just want to draw attention to that, and if you take nothing else away from this video, just think about that. The data needs to always be designed in a way that is optimal for its transformation. Because in this case, is this the most compact way to store this data? Well, absolutely not. 12 UN64Ts is 12 times 8 bytes. Right? So we have 96 bytes of data that represent the whole game board. We could easily do this in probably half, because if we chose to represent this from the board's point of view, say we still have 64 different squares to represent, how many bits would we need to represent a particular piece type for that square? Well, ignoring duplicates, we know we have 12 unique pieces for both sides on the chessboard, and then of course an empty square is also a type of piece, if you will. So then we have 13 possible values, or an ID from 0 to 12, which could be represented in 4 bits. Because 2 to the power of 4 is 16, that's the closest power of 2, rounding up of course, so that would mean that 2 squares could be represented by 1 byte of data, or each square by half a byte, 4 bits. So if you multiply that by 64, or in this case by 32, then you of course get 32 bytes of data that you could use to represent the entire chessboard instead of 96. So clearly more memory efficient, and to a lot of people that might seem like the optimal way to store this, because that's what we think about a lot when we try and decide how to store data. Can we make it compact? Now, why do we think that? Because obviously 96 bytes and 32 bytes are such negligible storage capacities that surely we wouldn't care about, yes, technically using 3 times more memory, but they're still just drops in the ocean compared to the amount that we have available to us. Well, one of the reasons is not just the physical storage requirements to store this data, it's also that transformation or manipulation that could happen to the data, because the more compact we keep our memory, generally speaking, the more efficient it can be to access it. The reason why, of course, is because when we retrieve memory from our actual physical RAM, it gets stored in our CPU cache. And the more compact that data is, the more of it we can store in our CPU cache. So technically speaking, smaller amounts of memory or more compact representations of data are actually more efficient. That by itself is a valid statement. It's completely true, but you need to be aware of the big picture, of course. What are you actually doing with that data once we read it? Because we know that reading it and writing it would potentially be faster if the memory is more compact. I say potentially because when you're dealing with such a low amount of memory, then the difference would probably be non-existent. But once you extrapolate that up, that's where you might actually see something. So just to give a really quick visual here, pretend that you are moving house. And so you have your little car here, which looks a bit like an airplane, and it's got a little trailer that you're using to tow all of your stuff. Let's say that each 32 bytes is like a little box. So over here in our trailer, we might have 1 box for the 32 bytes versus 2 additional boxes for our 96 bytes. How many trips do we have to make to and from our old and new house? Well, just a single trip, no matter what we use, because the amount that we're carrying is still small, even though, yes, it's bigger if we have 96 versus 32. Now, on the other hand, if this is the amount of boxes that we needed to transport, then suddenly you can see that if we just had a third of them, something like this, for example, it actually would be faster for us. It would take fewer trips because there's a finite amount that we can fit onto our trailer. And if we have much less, then that, of course, is better. So that's one of the reasons why pretty much everything that I will ever say on this code review series, and in general what we're taught in software engineering, is extremely dependent on what it is that you're actually doing. And even though, yes, using less memory, having a more compact representation of your data may mean that you can load more of it onto your trailer and actually process it faster if you were, say, iterating through all of it and doing some kind of operation to it. But you can see here that it depends on how much total data you actually have. Now, that's just step one. That's just the first thing to consider. The second thing to consider is, okay, well, I have my data. We've packed it into like these 32 bytes using 4 bits per actual cell. But now what does it mean to actually find out what piece is at a given cell? Because we can only address bytes as a minimum, right? So if we're at the bit level, we require bit operations to both read and write to that particular portion of the byte. Presumably, when we're evaluating possible moves for a chess computer, this is something that is extremely repetitive and performance intensive. Now again, I know very little about how chess computers actually work, so do take my assumptions with a grain of salt and feel free to correct me in the comments section below. But for this particular example, where we're using this minimax algorithm, we're going through and we're evaluating a lot of possible moves. The complicated thing about chess, of course, is that it goes deep. Because if we just take this pawn over here and we move it here, like, yeah, that might be a valid move and we might be like, oh, cool, but we can't actually see the impact of that move unless we simulate the other player doing their potentially optimal move, whatever that definition is. And then how do we combat that? How do we fight that? What's our next move? Are we trying to set something up? We can't look at moves in this sort of isolated, siloed context where it's just like, okay, this is a valid chess move. This achieves something this turn. Therefore, I'm just going to do that. No, we have to go deep and we have to look at lots of different possible sequences of moves. What's our opponent going to do? What's going to be the outcomes? Is this position preferable for us? It can go extremely deep. And of course, as we go deeper and deeper, it exponentially grows. And so chess computers typically have like a max depth that they will search up until. So even for something complex and popular like Stockfish, it will have like a max depth that it will evaluate moves to. And so what I'm trying to say here is that the amount of times that we need to retrieve these pieces, move them somewhere, evaluate board positions, this data is going to be very, very hot, right? Is very frequently accessed and manipulated. And so suddenly, even though we might have a more compact representation of that data, the operations that we might be doing to it may require more manipulation. It might be simpler for the CPU to actually look at a particular piece in a bit representation like this and just move it somewhere else. In fact, there are other optimizations for that in this very program, such as these like bishop and rook pre-generated magics that can be used to more efficiently evaluate potential moves for these sliding pieces. So this is just all to say that even though the data representation might in fact be more compact, if we have to do more operations to that data to actually run the algorithms that we need to run to transform it the way we need to transform it, then that might actually be the bottleneck and not like our utilization of the CPU cache. So how do you know? How do you know what to do if there are so many things to consider? That's why my number one advice for all of this stuff is test, write code. This isn't like constructing a building where you might make certain engineering assumptions and then when you actually build it full scale, you can actually see what happens. I mean, of course, there are simulations you can run for those engineering problems, but that aside, you're working in an extremely malleable environment of just code that you can compile, test on various hardware or platforms. So do that. Here's what university taught me. Theory is great. I mean, in my case, the theory we learnt about in university wasn't even particularly good theory. But anyway, theory is great. It's good to know theory, such as what I'm talking about here in this video. But nothing beats real-world data, real-world practice. I still think it's important to know theory, otherwise I probably wouldn't be making videos such as this. One of the reasons why is because you might write something and it might be either super fast or super slow or super average, and you might not have the knowledge, the theory behind that to understand why that might be. Knowing theory also leads to you making hopefully better decisions out of the box and wasting less time by having to go through and evaluate every possible solution you might be able to conjure up. At this stage, what we've been looking at here today has just been the data representation, not the algorithms, not the actual operations that need to happen to transform this data the way that we want to. And until we have that side of the puzzle, it's pretty much impossible to make an informed decision on just the data layout. I really like this specific example of representing the board from the point of view of the pieces rather than from the point of view of the chessboard, because I just think it's such a great real world example of how you sometimes have to look at this problem not from the point of view of your human brain, but from the point of view of the actual processing that the CPU is going to be doing to your data. Very often, students in university or high school who are learning programming are taught object-oriented programming, and they're taught to make classes which describe every kind of type of thing that they may have inside their program, because that kind of makes sense, I guess, to us as humans. We can visualize like these objects, we can create instances of them, which create copies of them. It kind of makes sense to us as humans. But then as we become more experienced, we realize that, yeah, that's also the thing slowing everything down, because we should be looking at this from the point of view of the actual hardware, of the computer, of the CPU, rather than our human brains. That's meaningless to us. Of course, there are so many scenarios, so many programs you could write where it just would not matter whatsoever if you structure everything optimal for the human brain or from the CPU, because the performance difference might be negligible. You might not be working on a particular problem where performance might matter at all. Because again, computers these days are fast. But if you're ready to kind of take that next step and become a better programmer, that's where you need to start thinking a little bit more like a computer and less like a human. This particular example here as well, as representing the board like from the point of view of the pieces, reminds me of arrays of structs versus structs of arrays. That's a very common debate as well. Not really like a debate, but just a way to look at the layout of your data. So an array of structs is when you just have like your object, for example, and then you just have an array of 50 of them. And your actual object might have like some data in it, such as like 3 integers, like a float, whatever it might be. And so when we have this memory representation, we've interleaved these two members. We'll basically have our data times 3 and then our float called value. And then we have the data times 3 and then we have another float value. And so we have like this interleaved layout, which if we're just trying to treat these as individual pieces of data that we might do operations on individually, meaning we might just have a function that runs through all of the values, all the floats and does something to it, or it runs through all the data of each object and it does something to it, we're suddenly skipping entire blocks of memory as part of our iteration, as part of our algorithm. However, if you instead take these two out, and so you just have all of your data here, which might be, 3 times, let's just say 50, because that's the example that we used over here. And then I might write this in orange. You have your float values like this, and again, you have 50 of them. Then now, of course, our memory layout is contiguous. We have our data times 3, data times 3, etc. And then over here, we have our float value, float value, float value. It's all tightly packed together. And when we iterate through that and run our algorithms over that data, we're going from one byte to the next. We're kind of fully utilizing that packed data rather than having to skip memory to get to what we want. And that, of course, produces more efficient code. It definitely makes more sense to us as humans to look at it from this way, but this might be optimal for our actual computers. And it's a very similar situation here where that board representation probably makes the most sense to most humans. But if we instead look at those algorithms and what they're trying to do, then representing it as a bitboard like this per piece might be optimal. Now, I'm assuming it's optimal, and that's why this person has gone through doing that. I know bitboards are generally like a thing in chess engines, and I'm guessing they're probably considered an optimization. But either way, I think this is a really good example. I hope you guys enjoyed this video. If you did, please don't forget to hit the like button. Leave your thoughts in the comment section below. I'd love to read them. Again, the main takeaway for this video is to always think about the layout of your data and memory with respect to the actual transformation of that data, the actual algorithms that are going to do something with that data. So far, I've been really enjoying going through this best C++ code ever. So if you'd like to see more of me looking at this particular code base and giving my thoughts, then please leave a comment below. I'll see you guys next time. Goodbye.